It's rolling.
It's recording, right?
It's rolling right now.
Yes.
Ah. So let's give him a second.
Yeah, learning new stuff. Live demo, let's say.
Yeah, like always.
Ah, there you are.
Okay, so welcome everyone. It's DataOps Poland meetup. Today, Jennifer is our guest, so I'm stopping the sharing my screen. And Jennifer, welcome on our stage. You are our star. Stage is yours.
Perfect. Thank you so
Go.
much. All right. I will share my screen. All right. Let's
Yeah,
dive
we
in.
see your screen. So
Perfect. All right, so I'm going to kind of hit high points today, but if you have any questions that are specific, feel free to toss them out in chat or accumulate them and ask me at the end. And then, of course, if you think of something outside of today's session, that's usually when the best questions always come up, right, is after everything's over and done and you don't remember how to contact that person again. My contact information is there in the lower left hand of the slide, and don't worry if you're trying to jot it down furiously or take a screenshot. It'll be on the next slide as well as the final slide as well. And I'm happy to send my contact info over to meetup organizers as well in case anybody wants that. So, but we're just going to cover kind of the high points of graph databases, really what you need to know, at least from a data ops perspective, as best as I can cover in the time allotted, of course. And then we'll kind of dive in and kind of go from there. So a little bit of background on me. I'm a developer and advocate at Neo4j, have been for the last over 4 years-ish now. I like to learn. I enjoy technology. I like to learn about technology, which is probably a good thing for this field, right? And then usually when I learn about something, then I like to share that with others somehow. So that usually kind of manifests itself as speaking at meetups and conferences, or writing technical blogs, or occasionally doing a video or something like that. And then on a personal note, there's a lot of different hobbies I enjoy, but most of them kind of boil down to I'm kind of a geek at heart, and I'm okay with that. So that's just kind of the last bullet about things I like to do outside of tech and my normal everyday work. So. All right. So most of us probably already realize that most things around us, our businesses, our applications, our everyday lives, are pretty much built on data, right? Businesses can't run probably without data. Industries rely on data. Governments rely on data. Economics, the rise and fall of economic structures, and even people rely on data. That's how we get to know other people and become friends, or maybe unfriend certain people because of data and things, the information that we accumulate, right? So data is really how we understand the world around us. Things like science, things like music, things like business applications, things like signing up for a class or for a video or anything. We rely on data. Data is how we learn. So whether that's through trial and error, okay, let me try something. Okay, that didn't work. That's another data point I can add. Or if I ask questions, okay, I know the answer to this question. I have another data point that I can add to my list. And usually the information that we accumulate over time then gives us better decisions and ways that we can make changes or maybe influence our actions or other people's actions along the way. If you've done some programming, like language programming, Python, Java, etc., you may or may not have read this book. I actually am working my way through it. I'm not done with it yet, but it's called Domain-Driven Design. And the whole idea here is understanding very well the domain, the data that you're dealing with underneath of your business solution or your project or whatever. And so your domain experts need to understand the domain very well and then help translate and communicate that domain and the terms to your business audiences, to your developers, to project leaders, managers, etc. And typically this happens over iterations. You become better and more acquainted with the data domain, and so do developers and data analysts and so on. And they build a better project or a better end result because they understand the domain that sits underneath it. So it gives you a better product. You're only building minimum functionality because you understand all of the data that sits at the bottom, and you're not building extra things that don't rely on that data, right? And it's also a good way as a developer to sanity check your code. You're only building functionality based off the data layer, that lowest layer of what's in the data, and you're not building anything else. If you've heard of the VASA, that's the ship on the right-hand side there. There's a couple of different approaches to data. You can have something that's very simple, basic, cut and dry, nothing, not any extra things need to get involved. Or you can have something that, hey, I have all this information, I want to do something with it, and maybe it's more than what's necessary. If you've heard of the VASA, the ship on the right, that is an excellent lesson in poor project management and scope creep. If you're interested, I actually flipped through and read almost the entire Wikipedia article again, just kind of refresh my memory. And it's a really interesting read. But basically, this ship was kind of thought up by a Swedish king back in the 1600s, wanted this grand, magnificent king of the seas ship. And there were actually a couple other ships that were commissioned alongside it, but this was kind of the flagship, if you will. And there were lots of things that happened. The king kind of changed his mind on what he wanted here and there. They went through like 3 different shipbuilders that were overseeing construction and designs. And of course, they made their own little handprints and imprints on the designs and things like that. And it ended up being, it made it about 1,400 yards. I forget the translation to kilometers. I apologize. That is in the Wikipedia article. But it didn't make it very far. Didn't even make it out of the bay before it sank. So it would not float. You had a little bit of a wind that kind of came through. And because it was so tall and so top heavy, the wind literally knocked it over, let water in where the gun ports were along the side, and the whole thing sank down into the bottom of the bay. So it didn't even make it on its first voyage. It didn't even make it to the naval base it was trying to reach. It just didn't even make it very far at all. And that's because it was not designed properly. It was over embellished. It was over designed, big, extravagant, lots of changes, and the project just did not work. It wouldn't even float, really. So we're on the right-hand side, or the left-hand side of the slide, excuse me. You have this very simple, cut and dry, lots of angles, solid foundation that should be able to hold up a building very steadily, but it's not, notice, very ornate or lavish or extravagant, but it'll hold the foundation of everything else built on top of it. So technical projects are kind of like this too. If you have kind of that base layer of good, solid data on the bottom, then all of your applications and other functionality that is built on top of that has a much better ground to stand on. Okay, so let's talk a little bit about data storage. Most of us are probably familiar with databases and data storage and all that sort of thing, but just kind of recap and figure out where graph fits in this. So databases at a base level definition is just a structured set of data held in a computer, usually one that's accessible in various ways. So whether you're dealing with relational or NoSQL databases or other types of databases, all of them will do this base thing, this core main thing. They're going to hold some sort of structure of data in the computer that you can access it in a variety of different ways. So probably the most common one that people think of is relational databases. This started back with Oracle in 1979, or at least Oracle was the one that made this kind of a big hit. And you have data organized into tables and fields, or rows and columns, if you will. And then you have kind of these joint operations or connections between them where you query across the tables. And the tables are linked via some kind of key structure or an indexing structure. The nice thing about this, compared to what came before it, is there weren't data model limitations. It was memory efficient for both read and write. Previous data stores compromised one and or the other. However, on the downside, it was very CPU intensive, and it had a difficult query language. SQL was something that was probably a huge learning curve. Any of us, even who, if you remember back to the first time looking at or learning SQL, it is quite a bit of a learning curve just to get the basic functionality down pat. I remember it being, for me at least. Then kind of came along the document database. MongoDB kind of made this famous in 2007 when they opened their MongoDB product. And this is a document database. So it's structured as kind of a nested JSON with properties and values and lots of nesting substructures, if you will. This, compared to relational databases, was pretty easy to query. The whole idea of document database, its kind of marketing slogan was no SQL. You were getting rid of that complicated, high learning curve of SQL. And it does have good horizontal scalability. So you can kind of spread documents out across machines or across regions. And that actually is pretty easy to do. The downside with this is you're still not dealing with a whole lot of flexibility. Your relationships are going to be pre-baked into the document. When you need to make changes to them, you're having to go into each document, grab the nested structure out, update certain fields, and then come back out again. So it's a little bit of kind of, dive, make the change, and come back out. So a little bit tricky when you're dealing with lots of nested relationships, especially. And then graph databases kind of came on the scene with Neo4j. Now, Neo4j did have a product, a library that was released in 2007 as well. However, it kind of hit the market curve a little later. I feel like somewhere around maybe 2010, 2011 is when you started to see kind of graph databases take off a little bit. And the good thing with this was that you didn't have CPU versus memory storage trade-off that you had in relational databases. So you weren't compromising either memory or CPU. Storage and memory is actually pretty cheap nowadays. And so that you weren't getting that massive trade-off as you got in relational databases. The downsides was that if you had a non-relational data set, so more static, maybe not connected data set, you really weren't getting a whole lot out of using a graph database. You still do have a query language. Just my personal opinion, it's easier than SQL. And I'll mention a couple of things as we go along. But it is still a query language. You're still needing to learn a query language to interact with the database, where maybe a document database, you wouldn't have that quite as much. Now, do you have to pick just one? You don't actually. It's called Polyglot persistence. And this is using multiple persistence strategies, each serving a different need. So you can have different types of databases to serve different business needs or strategic needs. It's basically just using the right tool for the job. Whatever data scenario you come up with, use the tool that best fits that data at the time. So that does exist. Neo4j is not so naive to think we need to exist in a bubble. There are lots of other data stores that need to be involved depending on the business strategy and solution you're looking at. Okay, so what is a graph? Let's just talk at a base level. What is this graph thing? So it's not really brand new. It's the technology actually is much older than the Neo4j release in 2007. As with most technologies, it arose from a solution need, both then and now. So initially, graph theory, which is kind of the basis of the technology, was founded back in the 1700s with Leonard Euler. He was a mathematician, scientist, inventor, as is typical of that kind of society at the time. A lot of your scholars were very well rounded and did a lot of different things. But he wanted to solve the 7 bridges of Königsberg problem, which was a puzzle, basically, that you had 4 land masses in the city of Königsberg, Prussia at the time. And there were 7 bridges that connected those 4 land masses. And the puzzle was if you could cross each of the 7 bridges, not overlap your path, and come back to the starting point. This puzzle actually is not solvable. However, the theory that he did, the graph theory, the point of your 4 lane masses or your entities and the connections or the bridges between them is what formed the basis of graph theory, which then kind of the technology much later on was based upon. And ideas such as graph theory, network science, there's areas of math and science that all use this. So it's not just kind of formed on its own out of nothing. And even when our CEO built the technology back in the early 2000s, That also arose from a business need at the time. The solution they were working with the data that they had was just not working. It was cumbersome. It was slow. It was awful. And him as a developer thought there should be something better. And so that's where graph database Neo4j kind of came into being. So as with most technologies, they're not usually just thought up just for fun or let's try it and see if it works. It arises because something you currently have doesn't work and you think there must be an easier way to do this. And so you build something hopefully better, right? Okay. So for instance, let's take a book domain, which we're going to deal with a little bit more here later. And let's say we want to find authors with reviews that on multiple of their books. So if you look at the kind of the data model drawing I've done here, you have books and you have reviews that were written for the books and you have authors who wrote those books or authored the books. And so if you'd want to find authors with reviews on multiple books, or if you'd want to find maybe the highest rated authors based on their books and their reviews and the scorings and all that sorts of things, that could be kind of cumbersome depending on the database you're trying to work with. You're going across multiple entities, you're possibly aggregating or calculating up scores for things, and you're pulling all those numbers back. And this is something that graphs handle really well. You're documenting not just the data, but the path to that data itself. You're answering how and why something got there. So why is this author the highest rated? Well, because they have 3,000 books, and of their 3,000 books, they have 50 reviews each, and 85% of them are 5 stars or something like that. You're understanding exactly how you're getting to that result. You understand the connections in the data, again, understanding why and how something got to be where it is. You could also find alternates and impacts. So let's say you're routing package shipping, and you have your main route is down or slow for some reason, and you want to find out, okay, how is that going to impact my normal delivery routes? Can I find alternate routes that might be shorter than the slowdown of the main one, etc. And so this is going to help you produce better assumptions. If my main route is down, then I can assume that I need to find another route, or I need to have my drivers leave earlier for their deliveries, etc. And that helps you make better business decisions. So let's talk a little bit about Neo4j specifically. I will also mention some other graphs and some other stuff out there. It's not just Neo4j. However, my experience, of course, lies mostly with Neo4j. So that's what we'll kind of focus on. Most of us, as data analysts, developers, data scientists, etc., want kind of the best of both worlds, right? We want the stability and consistency of solid, well-known technologies, but we also want to do innovative and really cool things with it, right? We want to improve, make our systems and applications better, faster, more valuable. And so most of us kind of want to sit in the middle of these two things. We want some stability. We want some innovation on that. And some of you may lean more one toward the other, and that's totally personal preference. But again, most of us probably sit in the middle somewhere. So there are some things that Neo4j does that or has or provides that kind of lean more with the stability of other types of databases, things that have been tried and true over the years. And then there are other things that are going to be new and innovative, things that nobody else has or very few others are doing. So let's talk a little bit about that. And I will mostly compare Graph Neo4j to relational databases, just because that's probably the broadest web of understanding for most people at this point. But I could compare document databases or columnar stores or key value stores or all kinds of other things too. We're just going to stick with graph and relational for right now. So ACID compliance, this is something that relational databases have and do provide on a consistent basis. ACID is atomic, consistent, independent, and durable. It basically just means good data integrity. You're not going to lose data between your writes and your reads. So if I write something to the database, I expect to be able to read it right back without losing that data somewhere in translation. Again, relational databases provide this typically out of the box. Almost all of them do, but not a lot of kind of quote NoSQL databases, and not very many graph databases do provide this. Neo4j is one that does. And then the thing that's different about Neo4j over relational is you're getting relationships at write versus read. So in a relational database, you're reading the tables and you're creating those relationships at query time. You're hopping across tables, you're consolidating and aggregating that data back into a full result set picture. Where in Neo4j, when you write the information or the data to the database, you're storing those relationships in the database itself, physical storage. And then when you read, you're just pulling out what's already there. So that's really the main difference between the two. And then both relational and graph databases provide scaling, both vertical and horizontal. So most of the time when you talk about vertical, that's scaling up the number of instances, read replica copies, if you will, where horizontal scaling is kind of your sharding. You're breaking apart your data into separate instances and then querying across all of those. Graph and relational databases both, most of them will provide both, and Neo4j is no exception to that. So in the blue, we have things that both areas of databases provide, and then highlighted there in the white is something that Neo4j and or graphs also give on top of everything else, or different from everything else. So that's the stability side. Now let's look at the innovative side. So relational databases have SQL, and Neo4j, several graph databases use Cypher. So this is a little bit different. It's just a little bit different of a query language. And we'll talk a little bit more about that, dive into kind of the syntax and what queries look like. We'll see plenty of examples here in the demo here later too. But their language difference, still a query language, but it is different a little bit. So, and then relational databases focus very hard on a very restrictive or schema enforced system. And this is to make sure that you don't have outliers, things that might potentially break queries or the data model or your data structures. However, the way Neo4j is structured, our system implements a schema-less or schema-optional system, which means that you're not forcing the data into a predefined structure when you put it into the database. That data model can adapt and move with you as your business needs change. We'll talk a little bit more about that too. And if anybody has questions, feel free to ask. And then also you get, with relational databases, you get ERDs or entity relationship diagrams. And versus in Neo4j, you get graph modeling, which we'll talk a lot more about in upcoming slides. But there is quite a bit of difference here. I've seen some pretty ugly ERDs. The one that I recall vividly was sprawled across like 2 cubicle walls worth of stuff. And it was a big, ugly system, all interconnected, all these, relationships and cardinality rules and such across all different kinds of tables. It was not pretty and very confusing. Hopefully graph modeling improves upon that a little bit. And then both systems provide lots of integrations, and you have both cloud and on-premises solutions. So whether you're dealing with something you want to run locally, or you want to integrate with other types of data stores, or maybe programming languages or tools and things that you're used to using, both systems have quite a wide variety of things that you could adapt and kind of plug and play into. So that's a nice thing about that. Okay, let's talk a little bit about the graph data model then. Property graph deals with nodes and relationships. If you're familiar with mathematical or network theory, graph theory terms, it's vertex and edge. Those are basically the same thing. We're based upon those principles. So nodes represent objects or entities. You can label those, which is basically like categorizing or grouping entities, if you will. And you can also have properties on those nodes. So here we have a book, an author, and a review. Notice this is the data model I showed earlier in the slides, and the data model that we're going to be dealing with when we get to querying and such. But you can have properties on these, which are kind of just more additional detail on each individual node. So you have our entities, book, author, and review. You have some information or properties that kind of hydrate or give a little bit more meaning to those particular entities. Then you have relationships. You have to have a type, or if you will, a relationship label or whatever. It's actually termed type. So in this case, we have a review is written for a book. The written for is the relationship type. And you have an author who authored a book. Again, authored is the relationship type. And you do have to store a relationship in a particular direction. We'll talk a little bit more. You can query either direction and it'll retrieve that relationship no matter what. But when you actually write it to the database, you have to tell it which way it's going from what node, what's the start and what's the end. You can also have properties on relationships too. So for instance, a review was added for a book at a particular date or time, or maybe you'd want to put other properties or detail on the relationship itself. You can absolutely do that. Nodes can also share multiple relationships. So for instance, let's say you have an author and a book, and not only maybe an author authored a book, but maybe the author mentions another book, or maybe an author mentions the current book, or the book mentions the author and links back to an author, or maybe another author or something. And so you could have multiple relationships depending on the direction. Here you can have vice versa. You can have multiple different types of relationships, etc. Okay, so a little bit more detail on labels. It's a group of nodes, kind of like a category. And you can also add multiple labels that then kind of subgroup and break the larger group into smaller groups. So for instance, I can label all of these nodes as person. I could also add additional labels to say, okay, these few people are also employees. These couple of people are also customers. And you notice you have this kind of one person in the middle that's all three. They're a person, they're also an employee who maybe has bought something from that company as well. So then they end up a customer, an employee, and a person as well. You can put multiple labels on nodes. That's not forbidden with Neo4j. It just allows you to kind of group and subgroup and slice and dice your data into different areas or groups, if you will. Okay, properties. They're key value pairs. They're associated with either nodes or relationships, either one. And if you've worked a lot with programming languages, it's kind of like a variable name with a value. That's how they're kind of formatted. So for instance, you could have a book ISBN. You could have the date a review is added. You could have the number of votes that review has, all kinds of things there. And there's lots of different property data types and all sorts of things with Neo4j. Okay, let's talk a little bit about our model for the demo that we're going to do. And this will kind of hopefully solidify some of the things we just talked about with the graph model. And then we'll kind of look at the query language and write some queries to kind of help solidify that as well. You may hear, or you may have heard, how graphs and or Neo4j are whiteboard friendly. What really does that mean? Well, typically, if you're dealing with a new data domain, or you're dealing with a new project, you'll probably go to a whiteboard or take out a piece of paper and draw the process flow or the data and the relationships between those data, or something along those lines. Most of us probably will default to a visual representation, right? And you usually draw circles with lines to connect them and show, okay, this passes through here and it goes over here and it hits this first and then it drops into this, etc. And so let's take our book domain. We have reviews and we have authors. And then when we store that into Neo4j, this is what the data looks like inside Neo4j. Now, granted, it's memory. Neo4j uses memory pointers, so this is a visual representation of what's there. But this is actually how the data is stored at the physical level. Notice how similar, actually exact, it looks from the original model we drew on the whiteboard to what's actually in the database. And this is kind of that whole idea between whiteboard friendly. The data that you put into the database, the model that you choose, is reflective of how the data exists in the real world itself. So why would you choose graphs? It's a natural data model match to the data as it currently exists in the real world. And of course, if that data model changes, if the data shifts and adds maybe more connections, or maybe it's no longer tied to this one thing, or it no longer has this constraint or this particular requirement any longer, then that data model can adapt in a graph and morph along with the business need. So you're not fitting the data into a specific format. There's no like, okay, let's make this work for the data model or for the constraints we have with our particular database. I've done that with relational models. I'd be like, well, this is how I would draft it out, but we have to have this unique value here. Let's add something to make that work, if you will. So the whole idea behind graph is that you don't have that scenario arise. You're putting the data in exactly as it exists. You're not modifying it to make it fit into the required structure. Now, I did mention there are other types of graphs. One of the big ones, so we talked about the property graph, the nodes and relationships with properties and labels and so on. There are other types of graphs out there. The most common one is Resource Description Framework, or RDF. And some of or most of you may have already worked with this type of data, but it organizes itself into triples, which is subject, predicate, object, which is basically node, relationship, node, if you will, just different terminology. It's usually web-based data, and you're often dealing in an XML format, but you're still kind of dealing with that entity-entity relationship, right? So it is a graph. It's just a little bit different from what the property graph model relies upon. And there are ways that you can translate between the two. Neo4j has some plugins and integrations that you can take RDF data and put it into the graph. And I believe you can also extract from the graph and export back out as well as RDF. Okay, so how do we query in a graph versus a relational database? What do the query structures look like? I'll show an example query, and then we'll actually dive into syntax a little bit. So this is SQL versus Cypher. Sorry about that. And so if we were to take our domain that we've been dealing with, we have books and we have authors. Author wrote a book. This would kind of be the query if we wanted to retrieve books and the authors related to them, or if we wanted to retrieve authors and their related books, we'd probably write some sort of SQL query like the one there at the top, which is select the book's ID, title, format, publication year, the author's name, and the author ID maybe. And then from book, and we'd left join onto that kind of associative entity table, because a book could be connected to more than one author, right? You can have a book that's written by more than one person. And then you have an author who has probably written more than one book. There's probably lots of those. So you have kind of a many-to-many relationship. And when you end up with that, you probably need a join table or associative entity table or lookup table, et cetera, however you want to term it. And so you'll do a left join on the kind of middle table there based on the middle table's book ID and the book ID you're getting from the book side of things. And then you'll join across on the author as well and connect the middle table's author ID to the author table's author ID in order to pull the related rows that kind of match all of those criteria, right? Where in Cypher, again, you're storing the relationship directly with the entities themselves. And so you don't need this lookup table. You don't need to kind of crunch across the IDs. You're grabbing the entities that you want, and you're going across the relationship and grabbing the connected entities on the other side. So that's why the pattern there looks a little bit simpler. That's why the query is a little bit shorter, et cetera, because you have that relationship stored and you're not having to do lookups across tables. And of course, if you're dealing with, for instance, my data set has about 10,000 books, over 12,000 authors, and that's just a subset of the full data set I pulled in. And so if you were querying across tables that were potentially hundreds of thousands or millions of rows long, that query could get more cumbersome. And if you wanted to pull reviews on top of that, it would get even more potentially. So that's one thing that Graph really does well across. This query is actually not that massively complicated. It's not that bad in SQL. If you're only dealing with 10,000 books, 12,000 authors, probably not that bad. But if you're dealing with hundreds of thousands or millions of rows on each table and you're doing lots of joins, that's where things get really cumbersome, potentially very slow. And that's what Cypher and Graphs have over relational databases in that area. So back to Cypher. Focus. I got off on a bunny trail there. So Cypher is both functional as well as visual. It's based on ASCII art, but it is also a declarative query language like SQL. It focuses on what to retrieve, not how to retrieve it. So for instance, we have kind of our graph pattern. Node A likes node B. And so we could do a match or find or select, however you want to look at it. Node A likes node B. And we'll talk a little bit more about syntax in the next couple of slides here. So if we wanted to create this pattern, Jennifer works for Neo4j. If we wanted to create that into the database, we have two nodes, right? One Jennifer, one for Neo4j, and there's a works for relationship. And this is the Cypher that we would write in order to create that pattern. So the create keyword, which is basically insert, if you're familiar with the relational SQL syntax, sorry. And then we need two nodes in a relationship. Now, our nodes are encompassed in parentheses. And if you take those parentheses and you bring them together, they form a circle, which is exactly the way that the entities are visualized as nodes right above it. So again, Cypher is very visual. Don't be fooled though. It does look pretty. It does look cutesy, but it is pretty powerful and has quite a bit of functionality involved there. So again, all of our node details are going to be within parentheses. And then our relationship, as you can see, the visualization there kind of has an arrow with this bracket or box that has the relationship type in the middle. If you look down at the query itself, you have kind of this arrow-like structure there with brackets around the relationship type, which looks pretty similar actually to the visualization right above it. Then within our nodes, we have some details we want to add. So we need a couple of labels to help categorize. Maybe we'd want to pull just our people and pull all the companies they work for. And so we could create labels, which are at the beginning there, specified with a colon in front of them. And we have a person node and we have a company node. And we can name this all sorts of things. We could call, instead of company, we can name it a business. We could name it a building. We could name it a who knows, country, works for a particular country. And then we could categorize Jennifer as an employee, or we could categorize her as a work from home staff, or we could any sort of number of things. We've just picked person as kind of our category there. And then maybe we want to specify a little bit more detail. So this person, this company has a little bit more information about it. So we specify properties, which are key value pairs or name value pairs that are specified within curly braces. There's also some other ways you can specify those. We'll look at that when we get to the query demo portion. But here we just have curly braces and our key value pair for our properties. Now, we've specified this, we've created this and put it into the database, or inserted it, if you will. Now maybe we'd want to query it back out. So I'd use a match keyword, and we know we have a person with a name of Jennifer as the property. We know there's a works for relationship coming from the Jennifer node, but maybe we don't know who she works for. Maybe we know there's a node on the other side. We want to find out who she works for. And so we could put this variable called whom in between the parentheses on the other side, and then return all of the details or all the information we have about that whom variable. In this case, because of the last slide and the query or the statement that we wrote to insert the data, because of the visualization we see, we know it's going to return Neo4j and all of the details we have on Neo4j. Okay, so let's turn it over and let's dive into the demo portion, and we'll actually query some data here. So let me take a quick peek at some comments and see if there's anything specific. Okay, no questions yet. Cool. If you think of anything, feel free to pop them into the chat. I will do my best to keep an eye on that. So I have some cloud databases here spun up. If you guys aren't familiar, Neo4j does have a new database as a service option, came out last year. And we do have free database options available for anybody who wants to just basically give their name and email address. You get a free Neo4j instance. You can load data. You can play with existing data. You can run queries. There's guides that walk you through how to work with graph data and what interesting things you can figure out with that data set, et cetera. Or, of course, you can load your own and write your own queries. But I'm going to turn over to this database here. Okay, I have to grab my password. 1 second. It logged me out after so long. I just tested this early this morning and it already logged me out. Okay. All right. Grab that. Okay. And connect to the database.
Now we know your password. Yes. 9 stars.
Yep, exactly. All right. And normally I save it, but I have multiple instances and I don't want to save over my other saved passwords and all that sort of wonderful stuff. So yeah. All right. That's the joy of having 2 screens, is you don't have to share your password while you're copy pasting it from another window. All righty. So let's just take a look at, actually, let me pull up the data model. If I've got graph. So let's look at how the data is organized. And as you see, it looks exactly like the screenshot I showed you in the slides. So this is how the data is stored in our database. We have reviews that were written for books. We have authors who authored or wrote those books. And that's the way our data is organized here in the database. So now let's try to look at, let's just pull something relatively simple here. Let's grab some books. So match books, return the, now I have about 10,000 books in the system. I don't want to overload my browser, my, the JavaScript that renders it. So I'm only going to pull about 50 just for a sampling. So I get this graph back. So notice there's no relationships. It's just our entities. But we get our nodes, and I can pull up all kinds of details. I can click on each one if I want to. And then I can look at all the details, all the properties, the key value pairs that we have stored on that node. So for instance, this one is actually rated pretty well. It's a 3.98 rating. There's the book ID, the country code is US. It's a hardcover format. There's an image. It's not an ebook. There's the ISBN and the ISBN 13 for the global categorization. There's a Kindle number. There's a link, the number of pages in it, the publication details, and then some ratings information, if it's part of a series, etc. So we get quite a bit of detail that we've loaded in. And if you're interested about the data set, I do have a link at the end of my slides. And then that will toss you out to a GitHub repo. And then there's some data load queries and things that you can just copy paste and load this data in for yourself as well. So we've got books loaded in, and so that looks good. But maybe, again, graph, you want relationships, right? That's the whole point of using a graph database, is to have relationships and to query across relationships. So let's now take this, and I'm going to copy it up to a new thing here, and we're going to pull the authors. So let's look at the authors that authored books, and let's limit to 50 still, just for I'm only returning book. Change that to everything. So books, relationships, and authors. So now we get this picture back, and I could actually zoom out a little bit. And there's some interesting things that kind of catch our eye. First off, you kind of expect a single book to be related to a single author, right? But you can see there's a few patterns here where you have multiple green nodes or author nodes connected to a single book. So these are instances where you have more than one author connected or writing a book. So for instance, this one here has quite a few authors. So if I click on this and kind of look at it, it is Servius's commentary on Book 4 of Virgil's Aeneid, or Aeneid. Not sure how to pronounce that, actually. I'll have to go study that up now. But you can see we have 4 authors. But if you look at this, you'll say, oh, it's a commentary. You probably have more than one author because they're each kind of providing their own comments as they work through the book itself. And so this is something that might be interesting, or maybe you'd want to study. But again, you're getting that context because, after all, you're looking at the title itself. You're looking at the number of authors there and go, oh, okay, this actually kind of makes sense because I understand the data now that's connected to it. You could do the same thing with some others. But let's kind of dive in a little bit and take a look at the flip side. So here we're looking at, you end up with, you have different authors working on the same book. But what if we wanted to pull and look at where authors wrote more than one book? So for instance, we could say where we have multiple patterns here. So we have a path where author here authored book. So I'm just looking. Okay, and then I'll explain this as I go. Give me 1 second. Okay, so basically we're counting the number of patterns, the size of where you have a particular path. In this case, where each author that we're pulling in this query here, each author has an authored relationship to a book node, and you're pulling back the entire path where that exists more than once. So for instance, I'm grabbing the same author. That's why I'm using the variable here, pulling all of their relationships to books and saying where I have the same author authoring more than one book. And now let's return all of those. Actually, let's tweak this a little bit. Let's return the author's name, and let's return the count of books that they have. And we're going to call this as count. And then let's see here. Yeah, let's do that. I need just specify as author, count, and then let's order by count in descending order. So here I'm just saying, okay, grab the author's name, aggregate the number of books based on that unique author name, and then order by the count in descending order. So highest number of books authored to lowest. So if I retrieve this, order by typo. Okay, so here, and I could even actually limit to only the top 10. So there's like 12,000 some odd authors. So maybe I don't want to pull 12,000 back. Silly me. This is what I get for talking and typing at the same time. Limit 10. Sorry about that. Okay, so now we get the top 10 people. We have Agatha Christie here at the top, who, at least in our data set, has written 19 books, which is quite a few. Then you have an anonymous, which is kind of interesting. And maybe we want to pull some queries and figure out, what this anonymous is, and if it's just something bad in the data, or if we actually have books that don't have authors that aren't written by anybody that want to remain anonymous. So you've got a few of those. Then you have Stephen King, which we know he did write several books there. But maybe we'd want to dive in a little bit on a specific person here. So let's look a little bit more about on Agatha Christie and her books that she authored. So let's take our first pattern here, and we'll keep with that. And then we want to specify a particular author. So she has a name, and we know the name is Agatha Christie. And let's retrieve her book titles. Title. And let's just pull the average rating of the book. And let's maybe find her best and her most rated books as rating. And I think it's ratings as count. And then order by, let's just order by the top rating in descending order, and then order by the count of ratings in descending order as well. So I'll explain a little bit of this. This title. Rating. Oh, I forgot by again. Man, my typo. Okay. Property key is not provided. Oh, okay. That's all right. All right. So, that's because ratings. What is this then? Rating count. Sorry about that. All righty, here we go. Much better. Okay, so here I'm grabbing Agatha Christie's books that she wrote. I'm pulling back each book's title. I'm pulling back each book's average rating. And then I'm pulling back the number of ratings that we have for that title. So for instance, we have The Mysterious Affair at Styles, the Hercule Poirot book, the first book. It has a rating of 3.98, which is really high. And it has a lot of reviews, almost 500. Then we're ordering by the rating. So pull the top ratings in descending order, so top to bottom. And then after that, after we've organized by rating, then we want to organize by count. So for instance, these two books here have the same rating. So we want to put the one that has more reviews on it at a higher place in line, if that makes sense. So we're aggregating based on multiple criteria that we can specify. So now we're able to see, okay, her highest rated books to lowest, and then the number of reviews each one of those got as well. And I'm going to pop over and take a look at questions here. Okay, so alrighty, so comment on the UI. Yep, browser is fun. It does pretty well most of the time. Has its little bugs, but yep, okay. And then somebody asked when you wouldn't choose graph like Neo4j for your project. There are a few instances. This is a really, really good question. And I've actually written an article that specifies, goes into a little bit more detail, but I'll kind of give the best I can off the top of my head. First off, if you are not dealing with a lot of relationships. So for instance, if you were to, let's say, expect you need to go across multiple different types of entities. For instance, maybe I'd want to query the length of time it took to ship something based on the product and the customer order and their preferences. So for instance, find something that in maybe the skiing industry, maybe those products take longer to ship out than other products. And is that because, you have a warehouse close by, or maybe you have to pull it in, you're importing those items and then shipping them out, etc. So that is one example. When you have lots of different types of entities. So for instance, in a relational database, you're going to end up with lots of separate tables, and you're going to need to query across those quite a lot. So either you're writing a lot of queries that do a lot of joins, or you're writing really big queries that do an absolute massive amount of joins all in one. Those queries typically get pretty cumbersome. They get weighed down and bogged down pretty quickly, especially when you have lots of rows on tables. For instance, if you're a big business that does a lot of orders for products, then you're probably going to end up with thousands, millions of orders, hopefully, right? Hopefully your business takes off and you're doing well. And so you'll have a ton of orders. And so querying across that order table to get to your customers or their user preferences or the shipping details, and going through those massive tables like that is going to slow down your queries quite a bit. So that's one example. When you have a lot of relationships or you're dealing with quite a few kind of large tables and you're joining across large tables quite a bit. So that's one example. Other situations would be, I thought of one just the other day. I had this question crop up. Things like reporting, if you're doing ad hoc queries, for instance, even if you have a lot of joins, but if you're running them once a month, or maybe annually at the end of the year to do reporting structures, that may not be that big of a deal to have something run a few hours overnight and have the report the next day. May not be that big of a deal. But if you're dealing with something that is not that way, it's a very system critical, you need real-time results very quickly, and then those joins and the big SQL queries become a problem. And so that's when something like Graph might help you avoid those types of situations. There is something else too. I'll keep noodling on that, and as soon as I think of the other use case, I'll bring it up. But the big one really is when you're not dealing with a lot of relationships, and so then you don't have that queries that do a lot of joins, or lots of join queries that run across really big tables. May not be that big of a deal to just leave those in a relational database. And there are a couple other situations too. Again, I have an article I can point people to if you're interested. I cover things that Graph is good at, and then I've got a section at the bottom that kind of lists off some things that Graph is not that good at. The big one is the relationship one that I mentioned. That's kind of the big go-to use case, that it's like, if you're not really doing relationship stuff or heavy relationship querying, then it's probably not necessary to go to Graph. Okay, so with this, the accuracy rating, grouping clause to get average and count. Oh, okay. Yeah, this is pre-calculated. So the data that I imported into the database already had those averages and the ratings and everything kind of aggregated and calculated. I could absolutely do like a count. For instance, I can write a query here coming up because I have the reviews. I actually can write a query coming up where we aggregate and count the number of reviews that we have per book, which is basically doing that aggregation on the fly at query time. Oh, I thought of the other use case now, just as I think of it. The other use case where you would not want to use Graph is if you're doing a lot of just number crunching. So for like reporting instances, or you just want to calculate averages or something like that. So say you have a ton of people, and maybe you'd want to calculate the average of their birth dates or something. Or maybe you'd want to calculate the average of their start date at your company or something like that. That is not something that Neo4j is optimized to handle, because it's optimized to handle traversing node, relationship node, relationship node. Where that type of query I just mentioned, in fact, I could write one, match a author. Turn average of a dot. Oh, what's a good author? Okay, so we could, yeah, let's just pull the average of average ratings. Well, let's find the middle of the road authors, right? So this query right here. Oh, sorry, hang on. So the two integer. This is stored, when I imported the data, it's stored it as a string. I have to go back and refactor the data. Okay, so the average rating is actually 3.359, et cetera, for an author. This is not a good query for graph because I'm not using any relationships. I'm grabbing authors and I'm calculating an average based on a property on that author. A relational database is optimized to handle this query because you're on one table, you're averaging up a single column based on all of the values in that column. So this is not well suited to graph because you're not utilizing the written relationship advantage. So this is another instance of where graphs aren't really optimized to do this. Yes, it can do it. it handles it fine. We have about 12,000 some odd author nodes and it calculated it up in 159 milliseconds. Not bad at all, but you're really not gaining anything from using a graph in this particular query. Okay, that was my other use case I wanted to mention. Okay, so those are really the big two where graphs really don't provide any extra advantage. So back to our Agatha Christie query, the values are pre-aggregated, so that's why I'm just pulling the values. I could absolutely use the ratings, and actually this is not a bad use of graphs because I'm utilizing the author relationships based on book ratings and book count. So I am traversing that relationship and I'm utilizing the aggregation based on the relationship and the number of patterns I'm getting back. So you may not get a ton of benefit from graph here, but at least I am using that relationship. So this might be an instance where maybe you'd want a proof of concept, the relational model version and the graph model version, run your queries and see what kind of performance results you get out of it. And then of course, if you're utilizing lots of hops across relationships, if you're utilizing other types of relationship data structures, then graph is going to give you the better advantage, where if you're not doing those things, then relational might come out the same for this type of query. So that's another thing you might want to look at too. Okay, so that was looking at Agatha Christie's best and most rated books. Now maybe we'd want to find the books that have the most reviews for her. So let's take and I'm only focusing in on Agatha Christie for today, but there's plenty of other authors in this data set we could look at. And this is a relatively scaled down version. So I have about 10,000 books or so, 12,000 authors, and I think about 70,000 reviews. The full data set is actually much, much bigger. I think it's well over 1 million books and multiple thousands of authors and like millions of reviews, maybe 2.5 million or so reviews. So I've scaled this down a little bit. We're not getting the full picture of everything that's in the data set. All right, so looking at Agatha Christie's books, we'd want to find the books that she has the most reviews on. So return the book title here, and then we'd want to count up. Oh, I actually need to write, her most reviewed. So I need to add the other piece to this, which is the reviews. Route 1, let's call this written for book, and then count up the reviews for each title as count, and then let's order by review, or just order by count, and descending order. Okay, so for instance, the aggregation question that was asked, this is taking advantage of the relationships that are currently in the graph and aggregating them at query time. So I'm not using that pre-stored count. So for instance, we have reviews written for books who Agatha Christie wrote, or that Agatha Christie wrote. We're grabbing the title for each of those books and we're counting up the reviews here using that same variable, counting up the reviews for those books and ordering by the number of reviews, the count in descending order. So these are her 2 books that were reviewed the most. There's really only 7 reviews out there that we have in the data set. But again, realize that this is a sub data set of the full structure that's available. So we may be missing some data, or there really are only 7 reviews for her top 2 books. So, all right. And so this is an instance of I'm aggregating at query time. Now, okay, we see that, we saw how her books were actually rated pretty well, 3.98, several reviews on some of these. Maybe we want to pull the most scathing reviews out of this and see which ones of her books really were not rated really well, and see what people said about them. Because maybe we'd want to figure out, okay, do we really want to read this book? What were the worst things that people said about these, right? And so we can write something like this, return the book title, like that, and then we'd want to pull the book's average rating. And of course, this average rating could update if we added more reviews and real-time data coming in. We could update these properties, or we could recalculate these properties at real time as well. This is just data that's already here as the rating. And then we'd want to grab the review rating as review, and then order by review in ascending order. So this is going to pull the lowest to highest. And then we maybe only want to return the top 5, let's say. So we're going to grab Agatha Christie's books that have reviews for them. We're going to pull out the book's title. We're going to grab the book's average rating, because maybe we would want to look at that and keep that in our analysis. And then we're going to grab the reviews rating as the review. Oh, I also want to grab the text. Review text as, you know what? I'm going to call this review. I'm going to call this review rating, and then order by the review rating. That's a little bit clearer, I think. Okay, so the ones that have the worst reviews, we have this Cat Among the Pigeons and Murder on the Lakes. Now notice these ratings are actually reasonably high, but there's a couple of reviews out there that are just scathing. First of all, this one might look like an accident, so it could be bad data, because this looks like this person read it when she was 12, he or she was 12, and has a good review of it, really loved it, but yet the review rating is 0. So maybe that person forgot to actually click the number of stars, or forgot to add a review, and for some reason the review let them submit that without choosing the number of stars. So maybe that's something you'd want to go back in your review system and say, oh, I actually need to fix that, because it allowed something to submit that doesn't have a review or a rating on it. And there's a couple, you can see there's a couple that we may have to translate. I'm not familiar with French, and I'm not exactly sure what language that is. But you can see that this one here is actually a negative review. So they don't like Hastings as a character. There's a reason that people remembered Holmes and Watson, but not Poirot. So this person actually did not like this book at all. Found one of the characters really annoying, and so they gave it actually a 0 review, which is pretty awful as well. But it could also be a case where they weren't forced to enter a one star. So that might be something to look at too. So maybe we might not want to read this book, or maybe we want to look at some of the other positive reviews and figure out, am I really interested in this or not? So we could look at that as well. Okay, let's pop back to our slides and kind of wrap up. Oh, I do have one question here sitting out in the chat. Optimizations like traditional relational databases, partitioning of data, similar to graph, anything similar in a graph database. So you do have some optimizations. You can create things like indexes. The difference with an index in a graph database, or at least in Neo4j, is that it helps narrow down a starting point. So for instance, I have created an index. I could actually show that. Oh, I lost my window. I hate when it does this. Okay. So I think it's show indexes. Yes. Okay. So I have a couple of constraints and I have a couple of indexes. Constraints automatically create an index as well. And so here I have indexes created on book, author, and review, where each of the IDs is going to be unique. So it basically says, hey, if I'm querying for a particular book, then it will grab the index off of book ID and say, hey, I need to start my query from this particular book ID and then move out in the graph from this point. So it tells you kind of a starting area of the graph to start traversing and grabbing patterns from that section. So indexes work a little bit differently, but they are going to help speed up those initial kind of lookups of where to start the traversal inside the graph. So that's one optimization. Partitioning of data, we do have that. So I mentioned vertical as well as horizontal scaling. So vertical scaling, you could add read replicas. So let's say you have a special instance that you only do your writes on. That's your kind of transactional database, everyday real-time stuff. And then you copy that data out onto read replicas that then you run all of your reporting or your ad hoc queries or other sorts of things on. So your read-only types of queries. That helps kind of basically break up the load and make sure that you're not running a bunch of read queries or somebody's not trying to overload your transactional system while it's trying to write data to the database. So that's one way. So that's one way you can kind of partition. The other way is horizontal scaling or sharding. And this is kind of breaking your data apart across separate databases or instances. The caveat with this is if you have something like relational model or document model, most of those are pretty siloed, right? You're dealing with single entities or single table, and you can kind of just dump that onto an instance and then query across, right? Because you're viewing those relationships at query time. However, with graph, you're storing those relationships in the physical storage. And so then you end up with kind of these spliced and diced graphs. There's a few different ways to do this that it still works really, really well. We have a couple of examples out there if you're interested in knowing more about how graph sharding works. But it kind of does pointers. So it'll kind of say, hey, you need to go over our this entity has a relationship to this other instance, and it connects over here based on this ID. So it's a little bit of a lookup. Realize when you do that sort of thing, you are going to get a little bit of latency and things that are introduced, as you would with relational or document or whatever. If you have to go across kind of instances like that. Graph is going to be a little bit different because, again, you have those spliced and diced and cut off relationships. Now, that doesn't always exist. There are some cases, for instance, the social media example that we use quite a bit in the sharding. You put all of your users, your social media users on one shard, and then you put all of their comments on another shard. And then you can grab kind of one or the other and query across them actually relatively fast and optimized. But it is going to be a little bit different than sharding with other types of data structures because you're storing those relationships in the database. Still workable, just different concerns, different things you want to worry about, and kind of take care in your data model, if you will. If there's other pieces about that you have questions about, other optimizations you want to know about the database or other things you can do, feel free to add on to that question or ping me later. I'm happy to kind of continue that and chat more on that. But that's everything I can think of right now. So, all right, let's drop back into our slides and wrap up with a couple of things. So first off, talk a little bit about the tools that Neo4j offers. We actually saw Neo4j browser. That's the query interface that I ran all those Cypher queries in, showed you guys the results. We also have a Neo4j Bloom tool, which is data exploration. That's kind of this, I don't know if it doesn't really show up. That's that middle screenshot with all the pretty orange nodes and yellow nodes and stuff there in the middle. And that is kind of a natural language query option. So for instance, I don't know if you can kind of see the query editor there in the upper left of that screenshot. You have author, book, review. And so you kind of specify, hey, I want to look at authors. I want to find their books and I want to see all those books reviews. But you're not using Cypher. You're not having to type specific syntax and worry about query errors and all that sort of stuff. So it's a little bit more natural language, very good for like data analysts, business analysts, and that sort of stuff. We have some import-export tools. So we have an ETL tool or a data importer if you're dealing with Neo4j Aura, so our cloud database. We also have the APOC library, which provides a ton of procedures and functions for importing data from all sorts of places. So different types of databases, from different tools, from flat files, from you name it, APOC probably has it. You can also write applications in various programming languages. So whether you're dealing with Java, .NET, Python, Go, all sorts of others, we have language drivers for a ton of them. A few of them are officially released by Neo4j, and then several others are driven by the community, either community members or our partner businesses and partner companies as well that have offered to kind of take up those language drivers too. As far as deployments, so we have our database as a service products. That's what I used today. You can get your own free instance if you want to go out. I've got a link on the next slide for that. You can run Neo4j in pretty much any public cloud. So Google Cloud, Azure, and AWS. You could also run locally. We have server installations. We have our Neo4j desktop, which is kind of a developer interface tool that runs instances locally in a more user-friendly way. And there's other sorts of options out there too, Docker and all sorts of things. Other things. So I talked a little bit about RDF. We have an integration tool if you're dealing with RDF data. If you need to mix and match data coming in and out of Spark, or work with data and Kafka, or pass Neo4j data to other places, Kafka can do that too. And we have tons others out there. Again, as with most databases, we have lots of things you can kind of plug and play and lots of integrations there. So there are probably options for anything you're working with, visualization tools, and all sorts of other things too. Okay, so wrapping up with a few resources. Neo4j Aura DB, which is our database as a service. You can go out to that link if you want to create your own free instance, play with either some pre-defined data set or load your own data in. It'll kind of walk you through and guide you through all of that as you see fit. If you want to know and want to use the data set that I used today, that's available at the second link. So if you want to get a better feel for what I used and how I imported it and all that good stuff, that's available. And then if you're interested, my blog highlights quite a bit of the work that I do on a weekly, daily, monthly basis on various projects I'm working on. I do tend to focus a little bit on Java and kind of Java ecosystem type stuff, but I've got a lot of data and import lessons learned and all sorts of other things too that I kind of enjoy sharing as well. As far as applications, I do have some applications if you're interested in something specific that are available via GitHub. So if you go out and just check out my main kind of account there, I've got a lot of different types of repositories there if you're interested in knowing more about applications and building applications on top of graphs. So again, my contact information there on the lower left-hand side, and I'll stick around and answer questions and happy to chat. Thank you guys very much for listening and staying, and hope to talk to you soon.
Yep. Thank you.
Thanks.
It's a good moment.